Hello and welcome to Unit 8, Lecture E, last section for kinetics and equilibrium. A couple of last concepts to wrap up this unit. The first one is the equilibrium expression. The product of the products raised to the power of their coefficients divided by the product of the reactants raised to the power of their coefficients. And looking at the example is probably the easiest way to understand that. So the example equation there that just have made up letters, there we have Q raised to the power of A times R raised to the power of B divided by L raised to the power of X and M raised to the power of Y. The good thing about this is they're not going to ask you to calculate any numbers based on this. They are constant values, which means in real use there would be data tables of them and they would tell you what temperature you're at and you would just use those numbers. The important thing for you to know is right here and here. So it says a large K value indicates equilibrium has more products than reactants. So if we have the product of the products on the top and reactants on the bottom, if we have a large number divided by a smaller number, you're going to have a K value that's greater than 1, and that's considered a large K value, which means your reaction is going to make more products than it has reactants left. The larger that K value is, the closer it goes to completion. So we talked about completion being non-reversible. If your K value is less than 1, which means you have a smaller number divided by a larger number, that means you have more reactants left, and this reaction is not something that happens very much. We use K values to talk about the solubility of things that are nearly insoluble. They would have very small K values, and they would indicate to you that they only dissolve a little tiny bit because you only get a small amount of your dissolved product. If we had to set one up looking at an equation, we are only going to use things that are aqueous and gases because those are the only things we can measure the concentration of. Pure solids and pure liquids have an infinite concentration. So if I were setting up the K value for the Haber process, I would say the concentration of ammonia raised to the second power divided by the concentration of nitrogen raised to the first power times the concentration of hydrogen raised to the third. And one of the ways that we can shift equilibrium is by changing the temperature, because reactions are either endo or exothermic. So if we add temperature, it favors the endothermic reaction and will shift your equilibrium equation. Be careful of those equations that have solids or liquids. If you were setting up an equilibrium equation for this example, we would ignore the solid magnesium, we would ignore the liquid water, and we would only have the concentration of magnesium chloride raised to the first power times the concentration of hydrogen raised to the first power divided by the concentration of HCl raised to the second power. Okay, best news is for your final exam, this is what you need to remember. You do not have to worry about setting up any of the equations. We're also going to talk about whether a reaction is spontaneous or not, and the definition of spontaneous is that the reactions will occur by themselves with no input of energy. But we know that all reactions have some kind of activation energy to get them started. What they mean by this with a spontaneous reaction is that they don't need anything extra than what is already in their environment. So if the air around them has enough energy to get them started without us having to add any extra heat from a burner flame, then that reaction would be spontaneous. So in order to understand how you can predict if something will be spontaneous or not, you need to realize there's two tendencies in nature. Having less energy, kind of like being lazy, we call energy enthalpy. So your delta H is enthalpy, H for delta H. So having a lower amount of energy is favored. That means exothermic reactions, which release energy, are going to be favored over endothermic reactions. There's also a tendency for randomness. Entropy is the fancy word we use for randomness. It has an R in it for randomness. The tendency in nature is for things to become more random. It takes a lot of energy to keep things organized and neat. You probably know that from your lockers and your bedrooms. So the tendency in nature is for things to become more random, and they use the symbol S. So we talk about a change in entropy Delta H's can have numbers to them. Entropy is just going to be either positive, meaning more random, or negative, meaning less random. All right, we've already talked about delta H, and we've talked about how you find it. It's products minus reactants. The heat of the products minus the heat of the reactants will give us our change in heat. You know that exothermic reactions have a negative sign for them then, and endothermic reactions have a positive sign. And we just said in nature the exothermic reactions are the ones that are favored. Entropy is randomness. When we talked about phases of matter, we said that solids are in nice, neat patterns. Liquids are random but close together, and gases are random and far apart. So gases would have the most entropy, and solids would have the least amount of entropy. And if we're dissolving something, so we have up here a solid and a liquid, and as it dissolves and it goes through this process and the pieces break off and scatter themselves around, it becomes more random. So down here at the bottom would be our aqueous solution. Aqueous is always going to be more random than the solid and the liquid that they started with. We can combine our ideas of enthalpy, having a negative delta H or exothermic being favored, and entropy, having a positive delta S being favored, into deciding whether your reaction is spontaneous or not with something called free energy. And it's called Gibbs free energy, so they use a delta G to talk about the change in the free energy of a system. The equation is that our change in energy is going to be equal to our delta H minus the temperature in kelvins. And what's important about that is that means that the sign is always positive if it's in kelvins, because there are no negative numbers in the Kelvin scale, times the delta S. So what we really need to look at are the signs of our delta H and our delta S to see whether they are going to be spontaneous or not. If your delta G has a negative sign, that means you have extra energy than you need, and the reaction will be spontaneous. So if we look down here at some examples, this is the easiest way to explain it. When we have respiration, so we have glucose plus oxygen making carbon dioxide and water. So we have a solid and a gas, we have a gas and a liquid. Our entropy is increasing, that's positive. This is an exothermic reaction. We know that from table I it gives off a lot of heat, so the delta H is negative. So I have a negative delta H minus a positive delta S, and that's always a negative minus a positive going to give me a negative sign for my delta G. So exothermic and more random reactions are always favored. Let's skip down here to the reverse of that, which is photosynthesis. Carbon dioxide and water becoming glucose and oxygen. A gas and a liquid becoming a solid is going to be less random, so it has a negative delta S, and this is endothermic, so our delta H is positive. So we have a positive delta H, and we're subtracting a negative delta S. So a positive minus a negative is like adding two positives together, and you are always going to get a positive delta G. So this reaction is never spontaneous, and that's why plants need sunlight for that energy to go in. If we look at phase changes here in the middle, then we're going to look at things where the conditions are important, the temperature. So if I have liquid to a solid is exothermic, it has to release energy, and going from a liquid to a solid is less random, so that's a negative delta H. Whether or not I get a positive or negative sign is going to depend on how large this value is. Because if I have a negative number and I subtract a small negative number, it'll still be negative. If I have a negative number and I subtract a large negative number, it's going to end up as a positive delta G. So whether or not liquid water turns into solid water depends if the temperature is cold enough. So if this number is small enough, if it's low enough, it will happen spontaneously. And then the next one, of course, is the melting of water. So I have my solid turning into a liquid. That's going to be a positive change in entropy, and it happens to be endothermic, so that's a positive delta G. Same thing here. This number is what it's going to depend upon. If this number at the end is large enough, so you're at a warm enough temperature, you'll end up with a negative delta G and your ice will melt. If this number is too small, you'll still have a positive delta G and it will stay a solid. That's it. Memorize the conditions that are favored and that aren't favored, and then the other two depend on temperature, and you are all set. They're not going to ask you to calculate this equation ever. And that wraps up kinetics and equilibrium.